We're now going to consider the creation of energy bands in lattice substances. But first of all, let's just recap what we know about atoms. We know that atoms have a set of energy levels which electrons are allowed to occupy. Each of these energy levels is associated with a wave function, and when we square that wave function, it tells us about the probability of finding an electron at a certain point in space. We also know that we've got the Pauli exclusion principle, which tells us that in each energy level, each state, we're only allowed to have one electron with a certain set of quantum numbers, where the quantum numbers are N, L, ML, S, and MS. So now, taking this picture of the atom, I want you to imagine that we've got two identical atoms and we bring them closer together. Now, as we bring them closer together, the wave functions for the electrons start to overlap. And when they do so, we can actually end up with two electrons in the same state. The problem with this is that it's excluded by the Pauli exclusion principle. So what actually happens is that energy state actually splits, and we end up with two energy states which are very close to each other, but a little bit distinct. So that's what happens when we bring together two atoms. Imagine bringing together n atoms to form a big lattice. In this case, those energy levels need to split into n distinct little levels which are all very close together. So this is known as an energy band. When we bring together large collections of atoms, rather than having just an individual energy level, instead we have a band which contains lots of distinct energy levels which are all so close together that we can't really distinguish them. Now, the overlap of the wave functions is greater for the outer electrons than for the inner electrons. The inner electrons are the ones closer to the nucleus. So it actually turns out that the band is much wider for the outer electrons than for the inner electrons. Now, we can use this band structure to understand some of the conductivity properties of different materials. So let's take an insulator such as diamond. In diamond, it turns out that when we look at the band structure, there's a completely filled band and then a gap and then a completely empty band. So this completely empty band, the lowest empty band, is known as the conduction band, and the upper filled band is known as the valence band. Now, why diamond is such a good insulator is that it's really hard to move the electrons from that filled band, from the valence band, up into the conduction band, and that's because there's a big gap between them. Now, in order to be a good conductor, we need to have electrons which are free to move. So this means that they need to be able to gain some kinetic energy if we apply a voltage across them. But because there's no nearby states that those electrons in that valence band can jump to, they can't get just a small amount of energy, they need to get a big amount of energy if they want to be free to move. It means that these insulators are very bad at conducting electricity. Now, in metals, on the other hand, it turns out that the highest filled level is only about halfway through the band. So this means that it's easy for electrons to gain just a little bit of energy, and then they've got some kinetic energy and they can move when a potential is applied. We have a special name for that highest filled, for the energy of that highest filled level at 0 Kelvin is known as the Fermi level. Now, semiconductors, you may think would be halfway between these two things. They actually turn out to be a bit more like insulators, but with a much smaller band gap. So in silicon, for example, we've got the valency band, which is completely filled, and then the conduction band, which is only 1.1 electron volts higher than the valence band. So it's quite easy for electrons to get enough energy thermally to be able to jump from the valence band to the conduction band. And that's why semiconductors actually become more conductive as we heat them up, whereas you hopefully remember that metals, as we heat them up, their resistance actually increases a little bit as there's more impediment to the electrons moving through the materials.